So good afternoon, everybody. I'm Itziar Angulo from the TSR Research Group from the University of the Basque Country. I would like to thank the organizers first for letting us participate in the conference today, and also Dr. Rogo for first inviting us. So as we are new to the group, I have prepared quite a general presentation in order to introduce ourselves and some of our previous and ongoing work about the characterization of the electrical grid as a propagation medium for PLC. So TSR stands for Tratamiento de la Señal y Radiocomunicaciones in Spanish. This is signal processing and radiocommunication. We are a research group based in the Faculty of Engineering in Bilbao, which belongs to the University of the Basque Country in Spain. We are a quite big research group with different research areas related to, for example, broadcasting, such as digital radio and television, wireless propagation, electromagnetic exposure, monitoring, or positioning based on signal processing. And some years ago, based on our experience with field trials and communication systems, and also thanks to a close collaboration with Iberdrola and ZIB, an important smart meter manufacturer here in the Basque Country, we started a new research area with two main objectives. First, the characterization of the power grid as a propagation medium for power line communications. So for frequencies above 9 kilohertz, this is to say characterization of the power grid in terms of impedance, attenuation, and non-intentional emissions. It is worth mentioning that we usually relate this characterization with the propagation channel for PLC signals, but of course this characterization is also important for other grid aspects such as planning or electromagnetic compatibility issues, etc. And then the second main objective is the analysis of efficiency and performance of power line communications and the design of new communication technologies for smart grids through the electrical grid and also wireless systems. So for the last years, we have developed several measurement systems for non-intentional emissions, grid access impedance, and attenuation. They are generic setups based on commercial equipment and then signal processing to measure this kind of supraharmonics, grid access impedance, and also transmission losses, originally on the frequency band from 9 to 500 kilohertz. But nowadays we have also developed a new measurement system that works up to 10 megahertz in order to also cover the frequency band used for broadband power line communications. So in this slide, we can see the last version of our measurement system for grid access impedance. So this system is able to characterize the time variability of the frequency-dependent grid access impedance within a fundamental cycle. So we can analyze the sub-cycle impedance. It is based on a digital oscilloscope, which is controlled by a laptop, and then a commercial signal generator. So first, a signal with certain frequency features is injected into the grid by means of this current coupler. And then we measure the current and the voltage that this signal generates in this well-characterized known branch. We also use a synchronization signal from the signal generator that is also recorded by the oscilloscope. And we also measure the 50 Hertz component of the electric signal in order to analyze those variations of the grid impedance within a fundamental cycle. And on the right side, we can see an example of the results that the system provides, the magnitude and phase of the impedance according to the frequency and also according to time. So we can see the time variability of the impedance. Using a previous version of our measurement system, we also carried out a study of non-intentional emissions generated by distributed energy resources. We developed several measurements in a microgrid that was composed of several transformation centers with offices and distributed energy resources such as photovoltaic inverters, also a hydro system with a power pump, a water pump, wind turbines, and battery chargers. So we characterized non-intentional emissions from these distributed energy resources. We can see an example in here with the voltage of these non-intentional emissions as a function of frequency. And we also characterized the frequency-dependent transmission losses that that a PLC signal would suffer in this situation. And then we analyze the interference on smart metering communications, and more precisely, the influence of these non-intentional emissions in the narrowband power line communications subnetwork topology. This was quite a controlled environment, but we have also developed field trials at the low voltage grids or low voltage grid from Iberdrola. So real scenarios in urban and rural environments. So we can characterize non-intentional emissions, both in the time domain and in the frequency domain. And we can see the spectrogram in here, and also the spectral characterization of these non-intentional emissions that are processed according to the CAI-SPR 16. So, for example, in this case, we can see a measurement location that where we can see harmonics of this 34 kilohertz component. And we also developed a statistical analysis of the level of non-intentional emissions for the different measurement points that belonged to the same type of scenario. So, for example, here we can see the statistical analysis of the level of non-intentional emissions for rural scenarios in this measurement campaign. So we can see the levels corresponding to the minimum, maximum, and then several percentiles. So the 10th, 50th, and 90th percentiles of the non-intentional emissions. We also participated in some field trials for the characterization of frequency-dependent grid access impedance at the low voltage grid in Switzerland. So we have the opportunity here to compare the results from our measurement system with the results from the measurement systems of the University of Applied Sciences and Arts of Western Switzerland and the Technical University of Dresden. So we can see an example here of the magnitude and phase of the frequency-dependent grid impedance and the results from the three different measurement systems, and we obtained quite similar results. So, and one of our latest studies is about the characterization of non-intentional emissions from electric vehicles and the influence of these non-intentional emissions on power line communications. So this study aims at evaluating these effects of the conducted non-intentional emissions generated during the electric vehicle charging process on the performance of narrowband power line communications. So we developed some field trials in order to obtain the non-intentional emissions from the chargers of two different models of electric vehicles. Then we characterize the non-intentional emission generated by these two electric vehicles, and we can obtain the characterization in terms of time and frequency again, and also the spectral characterization according to the CISPR16 method. So the advantage here, where we can see the time variability of these emissions, that we can, for example, analyze and see how these components that seem to be, let's say, broadband components are in fact narrower components that oscillate in frequency. And the second stage of this study is related to the influence on power line communications. So we reproduce in the laboratory these non-intentional emissions, and then we quantify the disturbance caused by these emissions on the quality of narrowband PLC communications. Oops. Okay, and just a brief mention about our participation in some international committees and standards organizations. We are currently participating in a working group from the European Committee for Electrotechnical Standardization, and also another working group from the International Electrotechnical Commission, with about signal processing methods in order to characterize supraharmonics from field measurements. And we also participated in a working group from SIGRE, where we contributed to the publication of a technical brochure about the assessment of conducted disturbances above 2 kHz in medium voltage and low voltage power systems. So that's all from my part. Thank you very much for your attention.